Welcome back to ECE 320A. This is a Monday, Tuesday. I'm confused, so this is a 75-minute class, I think. So I will try to abide by those rules. Today we're going to go through S-domain circuit analysis. We'll look at how do we transform these passive elements or put those into the S-domain, including initial conditions, and then we'll talk a little bit about why do we need two different kinds of representations if we do incorporate initial conditions, and we'll start analyzing some circuits. So let's go ahead and get started with S-domain representations, and tell me to speed up if, well, obviously I don't have a very fast gear or high gear, but I could try. Resistors. These actually go straight from time domain right into the frequency domain, and it's all because of Ohm's law, which says that V is equal to Ri. There is no time or no energy storage, no differentials, no integrals. It's just a constant relationship between current and voltage. And because of that, then in the S domain, this lecture is more exciting than I thought. We actually have background music. So we'll keep going. And we're assuming we have the passive sign convention, which means that in the S domain, here is our voltage relative to the reference direction of the current relative to a resistor R. If you've now defined a voltage and a current, then this is how those two are related in the S domain, just like you would think about them being related in the time domain. So that one is straightforward. Let's now go into the inductor. And Eli allows us to say that we have the voltage is proportional to the time rate of change of the current in the inductor, which now allows us to get a little bit more interesting relationship or connection between time domain and frequency domain. Now if we Laplace transform both sides of that equation, and this is one of the reasons why we went ahead and last time derived the relationship for the Laplace transform of a derivative, we can now use that. We now know that S times I sub L of S minus I sub L of 0 minus now needs to be included if, in fact, we have initial conditions on that inductor. We can distribute the proportionality constant, which is the inductance, on the right-hand side, and we now have SL times I sub L of S minus L I sub L of 0 minus. And you can now see that this voltage in the S domain on an inductor has two pieces. An impedance piece, here's the impedance, and a term due to initial conditions. Which means that if we now put this into our circuit and we are accommodating or taking into account the initial conditions on the inductor, then we need to make sure that we have both terms. We have the impedance term, SL. Here is our current. Let's define a reference direction for that. And now what we know is that this voltage of the inductor, actually, if you need to know the actual value of the inductor's voltage, you need to incorporate both pieces, both terms. You can't just say, oh, the voltage on that inductor is just due to the impedance SL. There's actually this initial condition piece. And how do we put the polarity or put the positive and negative signs inside that voltage source? We know that the magnitude of this is Li sub L at 0 minus. What I like to do is simply think about this in terms of a KVL and just do, okay, let's just do a KVL around that little mesh or around that little loop, which allows us now to say that we have minus V sub L of S plus SL times I sub L of S. And now what we need is we actually need it to be minus, so that tells us that we need this minus plus. We now need a minus Li sub L of 0 minus equaling 0, and this now gives us the same relationship on the expression for V sub L of S as we obtained by Laplace transforming both sides. We now know that V sub L of S is SL, I sub L minus Li sub L of 0 minus. And, well, somebody might actually want to write this in terms of a current source to accommodate that particular initial condition. And the way to see that is we don't need to throw this relationship away. We've just derived it. We might as well keep it. But now let's solve it for I sub L of S. Let's just now evaluate this equation for I sub L of S. And in so doing, we now see that we have 1 over SL times V sub L. And that's consistent now. To get an impedance, to get a current from a voltage, we would divide by the impedance. So that SL seems to be consistent with impedance in this formulation. We move the initial condition term to the other side. It now says a plus. We're dividing by SL, and now we have I sub L of 0 minus over S. And now we want to write or express this in terms of its circuit schematic or circuit realization, and that can now be done by saying, oh, here is our inductor current, I sub L. Let's define that, and now that's made up of two pieces. An impedance piece and a current source piece, where the current source now, if you think about writing KCL at that node, and here is our inductor's voltage, V sub L of S, then the first current up here is due to that piece. That's V sub L over SL, V sub L over the impedance of that inductor. And the next piece right here is now going to be, which direction do I need the source? I know the value of this initial condition term. That's now I sub L of 0 minus over S. Before, it was L I sub L of 0, no S involved. Now we have an S. And which way do we want to put this current source? Arrow. How do we reference that? To the left or to the right? With our KCL, we're simply saying what's coming in is I sub L, what's going out is that. And so now we're summing those two currents to give us the appropriate schematic of how we would now replace an inductor in an S-domain equivalent circuit with this schematic representation that accounts for the initial conditions. Why do we need two representations? Why don't we just use this one, or we just stick with this one? Is there any benefit to one over another? So the analysis, the answer was correct. Sometimes when we're performing analysis, one form might be more convenient than another. That's really the reason why it's nice to have the two. When we're doing, what kind of analysis would this that's now being displayed be convenient or more convenient to use versus the previous one? Now we're dealing with currents. That's kind of begging, node voltage analysis. If we're now doing node voltage analysis, this is the representation you probably want to use to incorporate initial conditions. Do you see, if you have zero initial conditions, that all you have to worry about is the impedance piece, SL? Here, obviously now if I ask, you would know, I need to be doing mesh current analysis if I'm going to put a series voltage source to accommodate my initial conditions. Yes? I was afraid of that. The question was, why did I use a resistor on one diagram and an inductor on another? Because I'm sleeping up here. It's an impedance. You could just put a box in there and say the impedance value is SL, but it's trying to be an inductor, so yes, let's just go ahead and give it an inductor symbol. But generically, I guess somebody could just put all of these as resistors and just give them a complex representation of SL, and that would still be okay, but it's better to just stick with what they are. This is now an inductor. Thank you. Any other corrections that need to be made or questions? And these are in your book as different figures. Let's now move on to the capacitor. Where ICE now gives us the current voltage relationship. We know that I sub C is now proportional to the time rate of change of the voltage across that capacitor. We can now put this into the S domain, and the derivation is similar. It's obviously different. It's dual to what we just derived. But if we now Laplace transform both sides, we have I sub C of S is now C times the Laplace transform of the derivative of the capacitor's voltage, distributing the C, and to make this look more like an impedance, we can now say, multiplication by SC is the same as division by 1 over SC, and we have minus C, V sub C of 0 minus. Again, we have the two terms, an impedance term and an initial condition term. We already have it in the form that's solved for the current. Let's now find its circuit representation. We now have the impedance of the capacitor, 1 over SC, and we have a current source. Here is our reference current direction for that capacitor. And here is the voltage. Again, it needs both terms. Now the direction is opposing, and its value is C V sub c of 0 minus. Again, you can make that determination of which way is the current source going by performing a KCL at the node where you have I sub c coming in, and going out you have the impedance or the current due to the impedance of the capacitor, and in fact the current due to the initial condition on the capacitor is actually going in and not going out, and that's the direction that the arrow needs to go, consistent with the minus c V sub c of 0 minus. If, and this then is for node voltage analysis, that representation, if we now solve this for V sub c of s, we can multiply both sides by 1 over SC. Again, that looks consistent with an impedance that scales I sub c. And then we have taking that over to the other side and multiplying by 1 over SC. We end up with the c's canceling, and we have then V sub c of 0 minus over S. And this one, in terms of its schematic to drop in to give us our S-domain equivalent circuit, we have our impedance 1 over SC. And now which way? We now have plus minus V sub c of 0 minus over S. And again, we need to make sure that we include both terms. If somebody now asks us what is the voltage associated with that capacitor. Let's work some examples with this information. So suppose we are given the following circuit. And this morning in class I said I was numerically challenged this morning, and I'm staying that way. All the element values are 1s. This is now true for t greater than or equal to 0. We're applying that input, which is an exponential, and let's suppose that we are actually given initial conditions. Let's say that the initial current through that inductor has been established and it's 2 amps, and the initial voltage on that capacitor is 10 volts. And we want to know what is I sub L of t, or what is the capacitor voltage. Why am I interested in those two? Oh, question in the back. The question was concerning the final exam. What was the previous? Well, you'll probably be allowed some kind of note sheet. How extensive or what form is yet to be determined, but if those previous circuit S-domain representations would make you feel more comfortable going into the final, that's something you might include on your note sheet. And then you would have to know, okay, how do I use that in my analysis? Question? So now can I assume that the inductor is a wire and the capacitor is open? Now essentially what we're doing is we have maybe external circuitry around this circuit establishing these initial conditions. And then when t equals 0, the switches get thrown in such a way that for whatever reason the current in that inductor is 2 and the voltage dropped across that capacitor is 10. I'm not showing you all the different circuitry external that would have to be involved in order to create those initial conditions. I'm just saying when you snap your finger at 0, when 0 occurs, you now have these two initial conditions on those energy storage devices, and you excite the circuit now with e to the minus 2t. So I wouldn't worry so much about how am I going to think about these inductors and capacitors. I'm just going to say, oh, I've now been given some additional information. Now essentially you have more than just one source. You now have these initial conditions acting like additional sources, essentially. And that's what falls into place when we start putting this into the S domain. We want to now find or say what is I sub L of t for t greater than or equal to 0, or V sub c of t, t greater than or equal to 0. Did that answer your question? I sort of didn't answer your question. I basically was saying, let's just assume that we're given this information, and then we have to live with that. The question was something about an inductor as a wire and the capacitor as an air gap. That's fine in terms of what they initially look like with the external circuitry created, but it could have been that at whatever was happening before, they just instantly appeared to have those initial conditions. We wouldn't have had to have DC sources interconnected in some way to produce those initial conditions. We could have maybe done it some other way, but all we know is that at time 0 plus, this is what happens, or this is what's happening. We want to now find I sub L of t as a function of time and or V sub c of t. How do we want to analyze this? Now I'm flipping back into my textbook and I'm going, okay, what are my choices? Right? So if you go all the way back, now I'm stressing my memory. Chapter 4 talks about analysis strategies with resistive circuits, but now essentially what we're doing is resistive circuit analysis, except now our resistors are a little more involved. They're now complex quantities. But it's kind of the thought process is just what we did in chapter 4, and that was mesh current analysis and node voltage analysis. Which one do we want to do? Mesh. Why did I know that was going to be your answer? We kind of, for whatever, and what do we know though? Which one can always be applied? Mesh or node voltage? Not with this circuit, but with any circuit in general. Which one can you always be assured will be applicable or can be applied? Both. Node voltage. Do I have the third option? Mesh. Mesh doesn't work with non-planar circuits. This is a planar circuit. I don't have wires crossing. Node voltage analysis always works. So we can always use node voltage analysis. We kind of like to always rely on our old standby, which is mesh analysis, but just letting you know, sometimes you do have to apply node voltage analysis. Let's now, and I'm just going to be generic. I'm not going to worry about subscripting this with, well, here's the time domain, so let me You know what one of my peeves is when you mix frequency domain and time domain in your expression. Referring to the final exam, that's a big no-no, okay? So don't have I of t's and v of s's floating around in the same equation. You either need to be in the time domain or the frequency domain. Either be in the kitchen or the living room. You need to figure out where you're working in order to solve the problem. So now I went back and said, oh, I'm just going to use a generic I. So in the S domain, that's going to be a capital I. And if I'm doing mesh analysis, I now know how I'm going to replace or represent those initial conditions. In my S domain circuit, I have my source, which was e to the minus 2t in the time domain. If I Laplace transform that, that's 1 over s plus 2. I have my resistor. That comes in directly as a 1. I had my impedance of the inductor, which was SL, and I said I was numerically challenged. L was 1. This is now S. I then have the initial condition, the impedance of the capacitor, and its initial condition. Now I need to go back and find on my note sheet what I'm using. I now need to use this. Or I'm now saying minus plus L, I sub L of 0 minus. L was 1. Maybe that was a poor choice because you can't see how it's all being impacted. It's not just the initial condition. It's actually the initial condition scaled by L. Here L is 1. But this is now minus plus, and that was a 2. Well, maybe I should say this. This was L I sub L of 0 minus, which those two together combine to give me a 2. Just as a reminder that this is L scaling the initial condition. It's not just the initial condition. It looks like it because the scaling is 1. And what's the other one? Now I have plus minus, and this is V sub C of 0 minus over S. And this was 10.
So when you gave the initial condition, you gave IL of 0 plus, and here it's 0 minus.
Oh, I gave IL of 0 plus and I sub L of 0 minus. Oh, man. What am I going to do? Do I need to worry? Does it matter? If it doesn't matter, why? Why does it not matter? One, why am I focusing on inductor current and capacitor voltage?
Those quantities cannot change instantaneously.
Okay, those are the ones that are the time rates of change. Those are the variables di dt and dv sub c dt and the Eli and ice. Those variables are continuous. They can't change instantaneously. So now we know that at 0 minus, whatever it was from our external circuitry, it's going to be preserved at 0 plus. Does that help? So, yes, maybe I was being a little sloppy, but I'm glad I was. It's the same. Okay? 0 minus and 0 plus. On either side of 0, those two are okay. But if we were worried about inductor voltage or capacitor current, then we would have to make sure we were doing the right or using the right value. Now let's write a KVL equation. We can now We said we wanted to do mesh analysis. We now have minus 1 over S plus 2, or the voltage drop. It's actually a voltage rise, so it's minus 1 over S plus 2, plus 1 times I, and I'm going to drop the argument S, plus S times I, minus 2, plus 1 over Si, plus 10 over S is equal to 0. And now you can see how those initial conditions actually look like sources. And you could use superposition if you wanted to. If all three of those made you feel a little nervous, you could say, let me look at them one at a time. It's a linear system. We can now use superposition and analyze the circuit with those three individually and then add them up at the end. Here, let's just carry them through and see how ugly it gets. Let's put all of the source terms on the right and collect our terms containing I. We now have, let's say, S plus 1 over S times I. And that's equal to 1 over S plus 2 plus 2 minus 10 over S. And make sure I do the algebra correctly. I can put this over a common denominator of S, ending with, or leaving me then in the numerator with S squared plus S plus 1. And if I get a common denominator over here, I end up with that expression. And this is why we need to be able to do partial fraction expansion or inverse Laplace. We want to eventually get this back into the time domain. But right now we're in the frequency domain. And we can now simplify this however you want to do it. Why don't I just go ahead and multiply through by everything, although I could cancel the s's on either side in the denominator, but I'll just go ahead and say I have s, and now I have quite a few terms here. Here's 2s squared plus 4s minus 10s minus 20. So that I now have 2s squared minus 5s, again, keep me awake, minus 20. Make sure the algebra, that's what we're doing now. We're just doing algebra, not differential equations. We're in the S domain. We're in the kitchen. So we're now doing S domain analysis. Downstairs, we now have S plus 2, S squared plus S plus 1. And those two can cancel. And this is some quadratic. It could have two real unequal roots, two complex conjugate roots, or two real equal roots to give us overdamped, underdamped, or critically damped behavior. This one, if we complete the square, we square that, we get s squared plus 2 times 1/2, or the 1s, plus 1/2 squared, which is 1/4. We're left with 3/4, which we want to write as something squared, and that's the square root of 3 over 2. Or we now know that the roots of that are now at minus 1/2 plus and minus j square root of 3 over 2. There's our exponential decay amount, e to the minus 1/2 t, and our damped frequency amount, omega sub d, square root of 3 over 2. Meaning this is now the minus alpha plus and minus j omega sub d that you should be comfortable with from previous classes. What's the structure of little I of t look like? Well, we can find that by doing a partial fraction expansion of this. Let me now write I of s as a partial fraction expansion. How many terms am I going to have? One, 2, 3, 4, or 5. We have 5 fingers. Now we can throw the dice. Oh, they're 6-sided on a dice, aren't they? We have 6 options. We have one term which is due to the pole at minus 2. And we have 2 possible terms due to these complex conjugate poles. One could be a cosine, which I'm going to now write as a b, s plus 1/2 over s plus 1/2 squared plus the square root of 3 over 2 squared. And I have another term, which is the exponentially damped sine wave, which is omega over s plus alpha squared plus omega sub d squared. This was now we okay with that? And we need generically to include both of those 2 terms. Because if we start exciting this system, we're probably going to have a cosine and a sine piece. They're both shaking at the same frequency, omega sub d, which is the square root of 3 over 2, and they both are exponentially damped with an amount e to the minus 1/2 t. And now on the final, if I said, what's the structure of the current flowing through that circuit? You wouldn't have to find A, B, and C. When I say structure, you just use A, B, and C as constants. Given enough time, I could find those. Right? The answer is yes. But here, if I just wanted the structure, I could say, oh, I of t is going to be a, e to the minus 2t. Now the structure involves e to the minus 2t. You have to show me that. Plus b, e to the minus 1/2 t cosine square root of 3 over 2t. Running out of room. Plus c, e to the minus 1/2 t cosine square root of 3 over 2 sine, and that's true for t greater than or equal to 0. Just with writing down that structure, do you see what I of t looks like? When are you no longer going to see SEE I of t? When will it be gone? I don't know. Let me plug it into my calculator. No, you don't have to evaluate it. You just need to look at time constants. You have 2 time constants here, and maybe unfortunately or fortunately they are reciprocally related. Sorry. One of the time constants is coming at us from that, and the other time constant is in both of these terms, and it's coming from that. We can now say, oh, one of the time constants, which I'm now in red, is 2t. What value of t, let's call it time constant 1, will that be 1? That's the definition of a time constant. In this case, that time constant, tau 1, is 1/2. And that's actually e to the minus 2t is much faster than e to the minus 1/2 t. You can kind of see those exponentials. The other one is now the 1/2 t. That one's now 2 seconds. And if we just agree with a shake and a nod that we'll say it's gone after 5 time constants, we're down to 1% of where we started after 5 time constants. That's when we assume we're at infinity. Kind of like to joke, let's go to infinity and beyond. It doesn't take very long in electrical and computer engineering to go to infinity. 5 tau, right? In this particular example, we look at the biggest tau, which is the slowest exponential, e to the minus 1/2, that's the 2. We have to wait 10 seconds. That's quite long, but we had a 1 farad and a 1 Henry inductor, 1 farad capacitor. Now, we're just showing you the process. That's what I was trying to say. We look at 5 tau of the slowest time constant, and that gives us how long we have to wait before everything is gone. What if, just for grins, we wanted to find A, B, and C? Oh, Mom, we learned our we found A, B, and C today. I'm sending you where? Back to preschool, Mom. No. We were doing partial fraction expansion, Mom. Oh, okay, that's better. What'd you get for A? How would we find A? First, we need to remember what the other side was equal, which is all of this. And set that equal to our 3 terms. And then solve for A, B, and C. A is now going to be the left-hand side, let's say, which was 2s squared minus 5s minus 20 over, I've now multiplied through by the factor underneath A, which was s plus 2. That's now gone from the denominator of all the terms, and I'm evaluating at the value of s that causes that factor to vanish, which is s equal minus 2. I now have s plus 1/2 squared plus the square root of 3 over 2 squared. I set that, or I evaluate that, and that's the A. The other 2 terms are gone because they were being multiplied by s plus 2, and I set s equal to minus 2. That now allows me to, and if I did the algebra right, which I'm not sure I would, trust me, you may want to go back, that ends up being minus 2/3. You simply evaluate that for s equal to minus 2, and you'll get some number. I obtained minus 2/3. What if we do B? Oh, The one standby is you could always put this all over a common denominator and get A, B's, and C's in the numerator, sprinkled around all of the different coefficients, and then equate coefficients on this with the 2s squared minus 5s minus 20 on the left-hand side. You'll get 3 equations and 3 unknowns. What we just did is we actually decoupled that and found A by itself. Can we find B? Well, let's use the strategy we talked about last time. Let's multiply through by s, all terms, and then let s go to infinity. And here it's actually infinity. It's not 5 tau. We're letting s go to infinity. What happens to the c term? It vanishes. It's c over s, and as s goes to infinity, we don't have c appearing. What about the a term? We have as over s plus 2 as s goes to infinity. That's as over s. That's a. It stays. The b, bs squared over s squared, b. That stays. The right-hand side now becomes a plus b, and the left-hand side is what happens to this in red as what? I've now multiplied it by s on the top, and I'm letting s go to infinity. What does that become? Two. So now this one I'm saying I'm going to multiply by s and then let s go to infinity, and I end up with 2 equaling a plus b. Or I've already found a. B is now 2 minus a, and a was a minus 2/3. B is now 8/3. We're almost there, and it really didn't take too much effort. What about C? We know this partial fraction expansion is valid for any value of s. Let's find a convenient value of s. Is there such a thing? Sometimes s equal to 0, but your s, if it's convenient, it can never be a pole. That's never convenient, because then you're going to end up with infinity equal infinity, and that doesn't give you anything. But here, a lot of times s equals 0 is nice or convenient. In this case, maybe s equal minus 1/2 is better. That eliminates b. And it's true for any value of s. And it doesn't cause the denominator to go to 0, which would cause everything to go unbounded. Here, a convenient value of s to find c . But you could let s equal 1, you could let s equal 0. You'll get a different set of numbers, but you better get the same c value. Here, doing that, I ended up with something. C is not quite as nice as the others, minus 12.7 with some more decimal places. Now I actually know what my I of t is. I of t is now minus 2/3 e to the minus 2t plus 8/3 e to the minus 1/2 t cosine square root of 3 over 2t minus 12.7 e to the minus 1/2 t sine . That's now I of t. That's the inductor current for time t greater than or equal to 0. What if we wanted to know V sub c of t? If we go back to our S-domain circuit, what are we looking for? Is that what we're looking for? Not quite. We need to include the initial condition, don't we? So in fact, V sub c of s would be this. What if we did find this? Let me call it V sub c hat. How would we find V sub c hat? That one, because we already know what the other piece is, that's 10 over s. So if we can find V sub c hat of s, we've got V sub c of s. We okay? What's V sub c hat? That's 1 over SC times I of S, and we already found I of S. And I of S was whatever it was up above. And if we went through all of that, we would end up with some numerator over S, S plus 2, S plus 1/2 squared plus square root of 3 over 2 squared. If that's the case, what is V sub c hat of t? Not V sub c of t, but V sub c hat. What's the structure of V sub c hat? Or maybe that's jumping too far. What's the partial fraction expansion of that? We okay with what I'm not including in the brackets? Could we find a hat? Because what's that say? V sub c hat. Well, what can you tell me about, now can you tell me the structure of V sub c hat of t? And this is a common exam question. I don't want you to spend time messing with finding A, B's, C's, B1, B2s. I want you to just show me that you understand the concept. You can now pull this into the time domain. And that's really, can you find a partial fraction expansion? And from that partial fraction expansion, those terms, can you identify what they look like in the time domain? So now we have an A hat, don't we? Just a constant. Plus a B hat, e to the minus 2t, plus a C hat, e to the minus 1/2 t cosine, square root of 3 over 2t, plus a D hat, e to the minus 1/2 t sine. Could we find A hat? Have you learned the final value theorem? No? Pardon? So if we knew the final value theorem, we could apply that to obtain this answer. We could find A hat without having to do all of that we just went through. We could just work with the transform expression for V sub C hat of t. The final value theorem tells us, so here's the final value theorem. This tells us that the limit in the time domain of V sub C hat of t as t goes to infinity is in fact equal to the limit as s goes to 0 of s V sub C hat of s. Now we wouldn't have to go through all of these gymnastics in order to find V sub C of t and then let t go to infinity. We could actually, we've already found capital V sub C hat. Let's now multiply it by s and let s go to 0. What happens when we do that? Here is our expression. Well, here's our expression. It's kind of not really done very well, is it? But this numerator we knew. Wasn't this the 2s squared minus 5s minus 20 beast? What happens when we multiply V sub C hat by s? Here's our numerator. We multiply it by s. I'm going to erase that because somebody will go, where'd that come from when they look at the notes? But that's in there. That cancels the s in the denominator. Now let's let s go to 0. What do we end up with? Upstairs, what's in the numerator as s goes to 0? The s squared vanishes, the s vanishes, we're just left with minus 20. What happens downstairs? Well, we've already canceled the s, so we're not blowing up by the denominator vanishing. That's accounted for with the multiplication by s in the final value theorem. We let s equal to 0, we get 2 times whatever is in the square brackets, and that's 1/2 squared plus the square root of 3 over 2 squared. And that's 1. That was fairly painless to find A hat, which is really what we just did. Using the final value theorem, we now have found the final value of V sub C hat. V sub C of t. We now have said that this is the limit as s goes to 0 of this mess, numerator over that. That ended up being minus 20 over 2 and 1. Minus 10. Right? But what is V sub c of s? That was Vc hat of s somewhere plus 10 over s due to the initial condition. Everybody had their Dramamine before they came to class, right? Motion sickness pill. That's now V sub c of s. And now we can see that V sub c of t, as t goes to infinity, is going to be minus 10 plus 10, or 0. That capacitor will discharge at infinity. Does that seem reasonable? So we now have looked at the limit as t goes to infinity. Because what happens to this term in the time domain? What's the inverse Laplace transform of 10 over s? And V sub c hat went to minus 10 in the limit. So the limit as t goes to infinity of V sub c of t is minus 10 plus 10, or 0 volts. Questions on that analysis? Let's find a transfer function. They're hiding everywhere, aren't they? So let's now find a transfer function. And you have no idea what I'm talking about if you are just listening to this, but that's your motivation to come to class. See what happens. Suppose we now have the following circuit. Suppose here's V1. And let's just keep it sort of generic. Let's say here's R1, here's SL, here's R2, here's R3, here's 1 over SC. And maybe we're interested in this voltage. Oh. I'm doing what I said you shouldn't do on the final. I just mixed the living room and the kitchen. Time domain and frequency domain. So this is now the input. Let's call it V sub 1 of S. And here's the output, V sub 0 of S. Do I need to worry about initial conditions if I'm worried about a transfer function, or if I'm finding a transfer function? No, I'm just interested in dynamic behavior, the relationship between V1, the input, and V sub 0, the output. If I'm trying to find a transfer function, I can neglect initial conditions. So now I can say I don't need to worry about the initial conditions when finding the transfer function. I'm really just interested in the dynamic relationship between the input, which in this case is V sub 1, and the output, which in this case is the output voltage across that capacitor, V sub 0. How do I find the transfer function? Perform circuit analysis. Okay, that's valid. What kind of circuit analysis? We could do mesh analysis, right? Mesh current analysis. We could say, oh, here's I1 and here's I2. And if I know I2, I can solve for V sub 0. And again, what did I say earlier on today? I said, you're really just playing in chapter 4. Except now you have grown up a little bit to the fact that now you can play with complex impedances, not just R values. We can now write two equations in the two unknowns, I1 and I sub 2, and solve for I sub 2, and then multiply that by 1 over SC to obtain V sub 0 of S. So if one approach, I should just say that you could solve this many different ways. Here we're saying two mesh equations because that circuit was planar. No wires crossing. We can use mesh analysis. We now have V sub 0 is equal to 1 over SC I sub 2 of S. What's the first equation? What's KVL around the first mesh? That's just like we've done it all along. It's minus V1 plus R1 plus what all do we have? SL times I1 plus R sub 2 times the net current down dropped is I1 minus I sub 2, and then we're back where we started. There's the first equation. The second equation, again, starting in the lower left-hand corner of that mesh, the drop in the direction of our mesh current analysis KVL equation, we're now going up. It's now R sub 2 times I2 minus I1 plus the other impedances times I sub 2. Or equation 2 now says we have R sub 2 I sub 2 minus I1 plus, what did we have? R3 plus 1 over SC I sub 2 is equal to 0. And now we simply need to do two equations in two unknowns. You could plug this in to a calculator, especially if it has symbolic algebra allowed, and you could invert a symbolic 2 by 2 matrix and find I1 and I2. You could, looking at the very first equation, you could solve that for I1 and then replace that expression for I1 in the second equation, and now we have an equation for I2 in terms of V1, which was our source. However you want to do it, it actually gets a little bit cumbersome with just variable names, but let's just say from 1, let me just do it a few more steps. From equation 1, we can now say that we have, all of the impedances that I1 touched, which was R1, R2 plus SL, I1, and that's now equal to R2, I2 plus V1. And you could solve that for I sub 1. And then plug that into 2. If I wanted to just ask now, what's the how many poles am I going to have in this transfer function between V1 and V sub 0? Can you tell me, or do you have a way of finding that? How many poles do I have? Or is that even a reasonable question to be asking? I'm sort of asking, what's the transfer function look like between V1 and V sub 0? Generically, how many poles would you expect? Or what's the order of that transfer function? Or how many energy storage devices do I have? That tells you the order of your system. This system is generically second order. You should expect a second order denominator. After all of this algebra, if you end up with a fourth order denominator, you better start investigating, saying, I must have made an algebra mistake. I should have only had a second order denominator. Here you can just start thinking in those ways to sort of say, okay, what's the answer in the back of the book? Or at least what can I sort of be thinking about approaching as far as an answer in the back of the book? One of the questions might be, how many poles would I expect to have? Or, said another way, what's the order of the denominator polynomial? That's consistent with generically. And why am I continuing to say generically? Well, you could have a, let's say, a series combination of capacitors or a parallel combination of inductors that effectively would collapse into fewer energy storage devices. Here, you have a capacitor and an inductor. Those aren't going to be combined. You have two energy storage devices. It should be a second order system. We should expect two poles in this transfer function. Another question might be, well, what would I expect? Now it might depend on what V sub 1 of time is. What if V sub 1 was a constant? What would I expect for a final value for V sub 0 of t? Can you make a comment on that? If V1 is constant or has a constant component, it could be made up of multiple terms, maybe an exponential. What if it was a sinusoid? What would you expect V sub 0 to be? It's linear. You would expect it to be shaking exactly the same as the input. Now I'm asking all sorts of questions. I have 2 minutes worth of questions. If we're paying it close to the time, I'm sure nobody's watching the time. You're all just focused, razor sharp on what's happening. What's V sub 0 of t if V1 is a constant? Do you have an idea? Now I'm going back to somebody's earlier question about wires and shorts. You never know, huh? What do we have? Can you tell me what's going to happen in the limit? Can you draw this circuit at infinity or for large values of time when V1 is a constant? The inductor acts like a wire. Capacitor opens up. You have a voltage divider. So now if V1 was in fact a constant or had a constant component, you would say, oh, in the limit, I better anticipate V sub 0 of t at big values of time being R2 over R1 plus R2 times V1's constant component. You know where you're going. You know how you're getting there because now you can say, oh, can I find the poles in this system? Now I know the structure of my response. It's critically damped, or it's overdamped, or it's underdamped. I know how I'm going to get to my final value, how I'm going to evolve. You can see quite a bit before you even begin the solution process. We'll figure out where we're going beyond today, beyond infinity, next time.